This is Kelly Freeman with A+ College Ready, and I want to introduce to you the first unit entitled Introduction to Chemistry, the Study of Matter. There are really two main physical sciences: chemistry, which is the study of matter, and physics, which gets the other half of the universe, the study of energy. You can compare the states of matter to a soccer field. If you think about a soccer field in terms of the people that populate it, the fans in the stands represent a solid. They're closely packed together, and they are moving, but they're moving in place, more like a vibrating. This compares to a solid. The people walking around the track that encircle the field are analogous to liquids. They have a more fluid-like movement. The particles are more spread apart. And instead of simply vibrating in place, they are actually translationally moving. And finally, the players on the field behave like gaseous molecules. They have the greatest movement, they have the most energy, they bounce off of each other, and they have great distances between them. Solids are rigid, they have a fixed shape with a fixed volume. Liquids are not rigid, they have no fixed shape, but they do have a fixed volume. While gases are not rigid at all, they have no fixed shape and no fixed volume. Solids and liquids can't be compressed, but gases can be compressed. So I want to introduce you to some important pieces of lab equipment that are commonly used in the lab. You also have a reference sheet which expands the options of lab equipment that you can be exposed to in the resources, and I suggest that you take a look at that. But in this PowerPoint, I want to mainly talk about some very commonly used pieces of equipment. The beaker. The beaker is used to store reagents and liquids. But most importantly, a beaker should never be used to measure reagents or liquids. It's just not a good measurement tool. Likewise with the Erlenmeyer flask, it's not a good measurement tool. Very handy for storing liquids. And the Erlenmeyer flask has the additional advantage of being able to, its shape allows you to swirl and mix reagents better than the beaker. The graduated cylinder is a very good instrument to use to measure. The evaporating dish is a solid piece of lab equipment. It's a ceramic piece of lab equipment, and generally ceramics can be heated to a higher temperature, can withstand higher temperatures than glass. So evaporating dishes are often used to heat substances. The Bunsen burner is commonly used to heat substances in the laboratory. The wash bottle is used to wash down reagents into the glassware. And we want to do a brief overview of lab safety. Of course, you should always wear goggles and aprons in the laboratory. You should always wear closed-toed shoes. You should always use a wafting motion to detect the odor of any reagent. Never ever put your nose directly over a reagent to smell it. If you're heating a test tube, you should never point it towards yourself or other people. Point it away. If you have long hair, you should pull it back, and certainly you should never eat or drink in the laboratory. An additional rule that you should follow is you should always wash your hands whenever you have lab, because even if you don't use dangerous chemicals during your lab, the people behind you or in front of you may use dangerous chemicals and leave the residue on the lab bench, and so you may come in contact with that and not even know it. So it's important to always wash your hands after you have worked in the laboratory. So let's see if we can find some places where these students are not obeying the safety rules. So this young man right here is eating in the laboratory. That's a big violation of safety rules. You should never eat or drink in the laboratory. This young woman has long hair that's not pulled back. She's working with a Bunsen burner. Very dangerous. This young man is washing his hands or possibly washing a piece of equipment. He doesn't have any goggles on. That water can splash up into your eyes, doing damage to your eyes. A big problem in the laboratory. Some things I see that are good are that these students are wearing aprons. And it looks like this young man over here has a pair of goggles on. And so some of the students are observing good safety rules. I want to overview the scientific method. I don't want to spend a lot of time on this because the assumption is that you have had the scientific method before you entered the pre-AP chemistry class. But I do want to review it. The most efficient way to learn the scientific method is just to actually practice it as you work in the laboratory. But the scientific method is a methodical problem-solving process that includes observation, and from your observations, formation of a question, the development of a hypothesis to address that question, the experimentation and collection of data based around that hypothesis, and the analysis of data to form a conclusion. A hypothesis reflects an educated guess about what will happen. It should be measurable. Whatever hypothesis you come up with should be a measurable hypothesis, and often, but not always, related in an if-then format. The data chart should be built around the type of data you need to collect. So students and teachers need to be reflective about what kind of information they need to collect in the laboratory based upon their hypothesis. It should be clearly labeled and all units should be provided. A data chart should only contain data, what you've measured or observed. Analysis is done using the data gathered. Analysis can take the form of a narrative, or calculations and manipulations of that data, or frequently a graphing of that data. Graphs of data include a dependent and an independent variable, frequently include a dependent and independent variable. The dependent variable is graphed on the y-axis, while an independent variable is graphed on the x-axis. The independent variables are factors that are changed on purpose, while the dependent variables are the factors that change as a result. So, for example, we have a problem here, or a hypothesis here. How will increasing the drop height of a ball in 2-meter increments affect the height of the ball bounce after it hits the ground? And so here we have the independent variable, and here we have the dependent variable. The dependent variable depends upon the independent variable. We're going to change this on purpose to see how this. Expressing the findings of your lab experiments in the form of a graph is one of the most effective ways to communicate what you have discovered in the laboratory. Graphs of data include a dependent variable, which is graphed on the y-axis, and an independent variable, which is graphed on the x-axis. Independent variables are factors that are changed on purpose, while dependent variables are the factor that changes as a result of the change in the independent variable. So let's look at an example. So here we have an hypothesis. how will increasing the drop height of a ball in 2-meter increments affect the height of the ball bounce after it hits the ground? So this is your independent variable. This is the variable that we're going to change on purpose. We're going to change in 2-meter increments. This is our dependent variable. This is the variable that's going to change as a result of changing the independent variable. The dependent variable depends upon the independent variable. So the height of the ball bounce depends upon the drop height that we start with our ball. So you try it. Here's a problem. Write a hypothesis for each of the following questions and then identify the dependent and the independent variable. Take a few seconds to think about appropriate hypothesis for this problem and then label the independent and the dependent variable. So one appropriate hypothesis might be if the temperatures are increased, the growth of radishes will increase. This is the dependent variable. The dependent variable depends upon the independent variable. The independent variable is grafted on the x-axis. The dependent variable is grafted on the y. Try it again. This is the independent variable. This is the dependent variable. The dependent variable depends upon the independent variable. The independent variable is grafted on the x, the dependent on the y. The periodic table is the most essential tool that you will be using in your chemistry class. It will be used throughout the course, and so you need to be familiar with the structure and the terminology behind the periodic table. There is a stair-step line that you should draw on your periodic table that divides the metals from the nonmetals. To the left of the stair-step line are all of the metals, and to the right are all of the nonmetals. Some of the elements along the stair-step line are metalloids. This is going to be really important as you go through nomenclature and bonding that you are able to identify a metal from a nonmetal. The periodic table is organized into groups and periods. Sometimes we call groups families because the elements in any one group share similar chemical properties. In terms of the periods, the chemical properties change as you move across any one period. Groups are columns going down, while periods are rows going across. There are 18 groups and 7 periods. The groups on the periodic table have some terms or names that you need to be familiar with. Group 1 are called the alkali metals. Group 2 is called the alkaline earth metals. And groups 3 through 13, this is a mistake, this should be 13. Groups 3 through 13 are called the transition metals. Group 17 are called the halogens. And group 18 are called the noble gases. They're called the noble gases because these gases are very unreactive and don't want to associate or bond with other elements on the periodic table. The elemental symbols on the periodic table have 1 or 2 letters. The second letter in any elemental symbol is always lowercase, while the first one is uppercase. While most of the elements have English origins, meaning that the symbol usually is pulled from the first or two letters of that English word. Some elements have Greek, Latin, or German origin and are kind of unexpected. For example, sodium comes from the Latin sodium. The word has the symbol Na. That symbol comes from the Latin term natrium. Some other commonly used elements that have different word origin include potassium, whose symbol is K, gold, whose symbol is Au, silver, whose symbol is Ag, iron, symbol is Fe, and tin, symbol is Sn. So now we're going to talk about how matter is categorized. Matter is categorized beginning with elements, compounds, and mixtures. Elements are pure substances that cannot be broken down into smaller units and still possess their chemical properties. The smallest unit of an element is the atom. And examples of elements include any element on the periodic table. Compounds are substances made of two or more different elements bound together. Some examples of compounds include water, 2 hydrogen, 1 oxygen, and salt, table salt, or sodium chloride, which includes 1 atom of sodium bound to 1 atom of chlorine. Mixtures are made up of 2 or more substances that are physically mixed but not chemically combined. Mixtures can be further categorized into heterogeneous or homogeneous. Heterogeneous mixtures are easily separated and not uniform. So an example of that might be simply a pizza. Pizzas are easily, the substances that make up a pizza are easily separated. You can take the pepperoni off, you can take the cheese off. While homogeneous mixtures are uniform and more difficult to separate. A good example of a homogeneous mixture are solutions of any kind. For example, a saltwater solution. You can separate a saltwater solution, but it's not as easy as separating a pizza. You have to go through the process of evaporation to separate the salt from the water. Particulate drawings are very important on the AP exam. So in order to be successful, you have to be able to interpret particulate drawings and also to create particulate drawings. And elements, mixtures, and compounds are a good place to practice that interpretation and creation of particulate drawings. So here we see an example of an element. They've used oxygen, and this is a little different because here we actually have 2 atoms of the same type bound together, and so we have a new vocabulary word here. This is actually called a molecule. C-U-L-E. A molecule of the element happens to be a diatomic element, meaning that there are 2 atoms that occur in the molecule. So here we have 1, 2, 3, 4, 5, 6 molecules of oxygen for a total of 12 atoms of oxygen. This is an element because they're all the same atom. Over here we have a particulate drawing of the compound water. So we have 1, 2, 3, 4, 5, 6, 7, 8 molecules of water. Any one molecule has 3 atoms, 2 atoms of hydrogen, and 1 atom of oxygen. So any one molecule has 3 atoms. We have 8 molecules, so 8 times 3 is 24 total atoms in this compound. Here we have a mixture. And we have a mixture. The mixture is defined as 2 or more substances that are not chemically bound together and able to separate. So Here we have a mixture of compounds and elements. These elements, because this is salt water, these elements happen to be in the form of ions, which we'll talk about later. But right now, we're going to just identify that we have 1, 2, 3, 4, 5, 6 molecules of the compound water. And we have 1, 2, 3, 4 atoms in the form of ions of sodium, and 1, 2, 3, 4 atoms in the form of ions of chlorine or chloride. So we actually have 1, 2, 3, 4 different types of atoms here. And we have 6 molecules of water that are made up of 2 different types of atoms. And we have 2 different types of elements in the form of ions, sodium and chloride. So let's practice this. Is X an element, a compound, or a mixture of elements and compounds? Think about it. X is an element. It's composed of atoms of one type of element. There are 4 of those atoms in this box. Well, excuse me, they're not 4, they're 5. 2, 3, 4, 5. There are 5 atoms in the box. Is Y an element, a compound, or a mixture of an element and a compound? Think about it. Y is a compound. We have 2 or more elements chemically bound together. We have 1, 2, 3, 4, 5, 6 molecules. 6 molecules of this compound. Each molecule is made up of 2 different types of atoms, so that we have 2 atoms per compound and a total of 12 atoms in Y. Is Z an element, compound, or a mixture of elements and compounds? Z is also a compound. 2 or more elements chemically bound together. There are 1, 2, 3, 4, 5 different molecules of this compound. Each molecule is made up of 3 different types of atoms, so that any one molecule has 3 atoms. There are a total of 15 atoms in this box. Is W an element, a compound, or a mixture of elements and or compounds? W is a mixture of elements and compounds. We have 1, 2 molecules of one type of compound. We have 1 molecule of another type of compound. And then we have 1, 2, 3 atoms of an element. One compound has 2 different types of atoms, while this compound has an additional 3 different types of atoms, so that we have a total of 10 atoms in the box. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 3 of this type of element, 2 of this type of element, 2 of this type of element, and then 1 of each of these types of elements in this molecule of this compound. The separation of mixtures is a very important chemical process and used in any laboratory research, forensics, chemical, medical. All of those types of labs will use the methodologies to separate mixtures, because we have to separate them in order to find out what they're made of. Some separation techniques include filtration, evaporation, distillation, and chromatography. This isn't all the types of methods of separation, but the 4 that we're going to talk about. Filtration is separation of substances using differences in size of the particles. A good example is this sand-water mixture. So we're going to filter the sand out of the water. The water will drop here, and the sand stays in the filter paper because sand is so much larger. Also used to separate an insoluble substance and a liquid, with sand being the insoluble substance and water being the liquid. Evaporation is used to separate a dissolved solid and a liquid. Salt water, which is what we've already talked about. This is an excellent way to separate a water-based solution so that the water evaporates out and what's left at the bottom is the salt. This is distillation, and it's probably the most interesting type of methodology to separate substances. Hold on, I'm trying to erase this. Give me just a moment. Whether it's being used in Jack Daniels in Tennessee to manufacture bourbon or in a moonshine still, distillation is a very interesting type of methodology to separate substances. It's based upon the differences in boiling points of liquids. So suppose you have a mash down here of mainly alcohol and water, and you need to separate the alcohol from the water. Well, alcohol has a lower boiling point than water, and so as you heat this substance, the alcohol will evaporate first. It will boil off first, and they'll condense it in a cooling coil, and it will drip down into your collection container. After you have boiled off all the alcohol, all that remains is the water. So you've used a difference in boiling point to separate these two substances. Chromatography is the separation of dissolved substances based on the degree of solubility. This is also a very common methodology used in all types of labs. So suppose you have a mixture of a substance here, and let's suppose that mixture is a water-soluble substance. You place it on a medium. In this case, it's simply paper chromatography. And you place the paper in a solvent. And if these are water-soluble, then it will be water. The water will creep up the paper medium. It will dissolve the mixture that you've placed. And as the dissolved substances in the mixture creep up the paper, they will deposit themselves according to their degree of solubility in that water, with the most soluble substance rising highest, most soluble rising highest, and the least soluble rising the least. Physical and chemical properties and changes. Physical properties are observed without changing the composition of a substance, such as melting point, boiling point, density. These are physical properties. While chemical properties are observed as a substance undergoing a change in composition. An example of a chemical property is flammability. The difference between physical and chemical changes. A physical change doesn't affect the composition of that substance. So if you cut something in half, that's a physical change. If you melt it, that's a physical change. You've got water before, you've got water after. You had liquid water, then you had solid water, or you had solid water, then you had liquid water, but it's still water, physical change. When you have when you have a chemical change, you have a brand new composition, a brand new substance with a new composition at the end of the change. Example, cooking something is a chemical change. You put in eggs, you put in flour, you put in milk, and you cook it. At the end, you have a cake. You can't pull the eggs back out. You can't pull the flour back out. You have a brand new substance, a different composition. It's undergone a chemical change. So, here's some questions to help you put that concept to use. Cutting bread, physical or chemical change? This is a physical change. The substance is the same before and after. It's smaller, you've cut it, but we still have bread. Bread before, bread after. Physical or chemical change, the rusting of nails. So these nails that are made of iron have rusted. No longer do we have just iron, we have a new substance, iron oxide. We have a substance that has a new composition. Because we have a new composition, different from what we started with, this is a chemical change. Extensive properties are properties that depend on the amount of matter in a substance, for example, mass and volume, while intensive properties do not depend on the amount of matter in a substance, for example, temperature, solubility, and density. Endothermic reactions are reactions that absorb heat. If you were to feel an endothermic reaction, it would feel cool because the reaction is pulling the heat from your hand, and so it would feel cool. If you write an endothermic reaction, the heat appears on the left side of the reaction, of the yield sign. So here is an endothermic reaction appearing on the left side of this yield sign. And exothermic reactions are reactions that release heat. If you were to put your hand on a beaker that had an exothermic reaction, it would feel warm because the heat is moving from the reaction to your hand. When you write an exothermic reaction, you represent the heat on the right side of the reaction. These are energy curves, and you'll see these a lot throughout your time in chemistry. Here we have energy on the y-axis and time. We'll just put time on the x-axis. And here are the reactants, and here are the products. So as time moves along and the reactants are changed to products, obviously what's happened is we've gained energy. The products have more energy than the reactants. Well, where did that energy come from? It had to come from outside in. So because the energy is moving from outside the system to inside the system, this is an endothermic reaction, where the products have more energy than the reactants. Over here on the exothermic energy diagram, again we have the reactants here and the products here. Well, as time moves on and the reactants turn to products, obviously the products have less energy than the reactants. Well, what happened to that energy? It had to go out. When the energy moves from the reaction to the surroundings, from the system to the surroundings, we call that an exothermic reaction.